In this video, I'm going to show you how to take a Hall effect sensor and make a NOT gate. And I need a NOT gate for the first part of a DC motor project. And this is going to be a brushless DC motor project. Now, Hall effect sensors come in a variety of packages, and here's some that you can buy that already have their leads. Unfortunately, the ones I have are surface mounted, so I had to reflow mine onto a board and then solder on some leads onto the board. So if you already have a Hall effect sensor that has leads, then you can skip ahead. But if you don't, then you can see how you can solve the problem with a surface mount sensor. So for this particular project, I don't have any video of how I reflowed this, but I have another video that explains it. And it's so small that I had to almost use a microscope. It kind of felt like performing neurosurgery on a rabbit or something. I don't know. But anyway, I got a piece of tape here and a magnifying glass so that I could see on this tiny board. And here's how I soldered on the leads. And we have three. We have a supply, VCC, a ground, and then the output. And the white is going to be the output. Now let's take a look at the spec sheet for the typical application for my sensor. My sensor acts as a switch. And so it isn't variable, it's either on or off. It's a digital output. And so in order to have the output equal to the VCC, you just need to put a resistor between the supply and the output. And then when it sees a north pole only, then it will go low. Otherwise it stays high. And this is the opposite of what I need. I need one that goes high when it sees a north pole. So here's the first circuit that I just built, and the white is the output, and when we put it up to the power supply, it's going to show 5 volts, which is near the supply voltage, and it'll be this whether there's a magnet there or not, and that is not what we want. Now when we pass a magnet in front of it, then the voltage goes to 0. So we need to swap that, and to do that we're going to use what's called a NOT gate. So a NOT gate basically takes an input and makes the opposite of what it is. So if you have plus 5 volts as an input, then the output will be 0. Likewise, if you have 0 as the input, it'll have 5 volts as the output. And so that's exactly what we want to do. So in this diagram right here, the resistor at the top, the one I used is a 47 kilo ohm. And I didn't use a resistor into the base because my output is basically voltage and very, very little current, so I don't need a resistor going into the base of the NPN transistor. So here I'm going to take my voltmeter to the output of the NOT gate that I just built, and let's do the same test. And as you can see now, when we pass the north pole in front of the Hall effect sensor, we have a 5 volt output, and that's perfect. Now, if you looked at the last video I did on IGBTs, you will know that you can use an IGBT as a voltage-controlled switch. Now remember, the output of my Hall effect sensor is digital, so I can't even drive an LED directly from it. So I'm going to take the IGBT and I'm going to use it as the switch so that I can power an LED so that we can see what's going on. Alright, now let's take a look at this in detail and see what's going on here. So here's our Hall effect sensor. And the red wire is the power supply, the black is ground, and the white is the digital output. So we have the resistor, as I showed you before, from the positive power, and then we put the output at the low side of that resistor. And so now so at this point, with no magnet here, this is going to be 5 volts, so this will be high. Now, so we're going to run the white wire, which is the output, into the base of an NPN transistor right here, right there. Now to make the NOT gate, we go from the power supply through this resistor, and then we're going to tap into the output right there at the base of that resistor. So now I like to use white as the output because it makes sense to me. And so now this is going to be flopped. So at this point, when there's no north pole here, this will be 0. And you can see that because I've taken this IGBT, which in this case we're going to use as a voltage controlled switch, And the gate is pin 1, which is the white lead. And then the output is going to go right here through a resistor into this LED. Now we take our magnet, and it's not marked, so I have to just test. I don't know which is which. So that must be positive. So as we pass it in front, then we're going to get the switch to come on. And when we take it away, it's going to be off. And if we flip it around, and we have the south pole to it, nothing happens because my particular Hall effect sensor is only active on a north pole only. And then what we can do is that we can now determine the position of the armature. So if you take this and you put this on a DC motor and this is spinning around, we will now know exactly where it is in its path. So if you look at a typical DC motor, the brushes determine when to turn on the magnetic field. So the advantage here of a brushless is that we don't have the resistance and all the problems that brushes have, and we can determine electronically where the armature is and then know exactly when to turn on the magnetic field. So stay tuned for updates and you can see what kind of progress we're making on this DIY brushless motor.